Martin, you had a question. Did you figure that out? So
it comes down to what happens at the axis crossing.
yeah. So the good news is, so I think we can put maybe the coordinates somewhere in the center. This is Z. Is that thick? What is the thickness?
From positive A to negative A.
So this much is A, and so this is the origin, and this is negative A, right? So, and there's K coming this way.
J coming.
J,
The whole
sorry.
thing is
Yeah,
J.
J. And so J is some J in the X hat direction. So again, I think yeah, this is true by symmetry. If it's true for a plane, you can stack up the planes. Yeah? And to get the outside field, what you would do is get an Amperian loop this way. Let's call this some L. So the contribution would be here and here. So B times B, if it's equidistant, the magnitude would be the same, right? So 2BL is equal to mu 0 JL times 2A. Yeah? 2A being the thickness. L, of course, goes away. And why is it 2A? Because there's current only in this region, even though you're outside. So then you would get B equals what? Mu 0 J A, correct?
Yeah.
So that means B above there's no divided by 2 here, because there's a 2A here. And B below this is outside. Right? For inside, you just pick a loop that is both inside and outside. Huh. So far, so good?
Yeah.
So let's pick this loop. And let this distance, oops, that's not true. Let this distance be Z, and this, of course, is A. So then, and again, we'll do this. So this one we know. What is that? So if I go this way, the minus and minus is going to cancel. I'm going to get mu 0 JA times L minus B below, whatever that is. Yeah? Or rather, plus or minus will make it clear. B inside times L is equal to mu 0 J, L's cancel, and I would have A minus C. This L is an artifact of the Amperian loop, so it goes away. And in fact, this term and this term is exactly the same, so I would get B inside to be minus mu 0 J A Z in the So notice B inside is in the negative y hat direction here. And the same argument is true just all the way through, regardless of, and B here because Z is 0. And then for negative Z, B changes character. Yeah? Very good. Good?
How did we keep our A in our B, in our final B in state? If we're saying that those two terms are the same, we subtract it off. That A, should that A be there and B inside?
Where B?
Last line,
Nope.
should just be,
Yep. Just straight out algebraic error. Thank you. Skipping steps. Always dangerous. Okay, so I want to complete a discussion that we started. So if we have a surface with some K, we worked out boundary conditions essentially by looking at a small rectangular patch, and all boundary conditions, the discontinuities come from a very local patch, because faraway currents do not create discontinuities. It's only currents where you're located, just like electric fields. And from this, we have surmised that B above minus B below is equal to mu0 K cross normal. I want to make sure that this is in fact correct. I think that is sort of where we stopped last time. Just making sure the sign is correct. Is it?
The only distinction you have is that we were specifying above, but you said any direction we choose is our
No, correct. It is true, but above is decided by what we pick the normal to be. I mean,
So it has to be consistent with the normal, that's what.
consistent with the normal. Yeah. The normal, if you are in space, there's no up or down, right? So what's above and what's below, it may not be clear. If it's a closed surface, there's something to be said about it. There's inside versus outside. So here, the consistency is in the direction of n. Now the question is, what about the potential? So, first of all, you just by doing, see, B equals del cross A, and from here, I think we did it for the solenoid to get the the vector potential inside the solenoid. You would have A dot dl equals just magnetic flux, right? B dot dA. Clearly, B can be discontinuous all at once, but as A goes to 0, the flux goes to 0. So suppose you have this sort of a discontinuity. And I don't care what area you take. Maybe you can even take a nice little rectangular, the usual pillbox. Oh, sorry, it's it's the Amperian loop you're taking. So let me show that this way. There's a current over here, right? So here there is K, which is say coming out of the page. This is a cross section of the surface. Then you take an Amperian loop here, and you're doing A dot dl. Yeah, and then it's the flux, it's the magnetic flux coming out of this area. So let me put that. Through the area. That's what this is. Now, B may be discontinuous, but it's still bounded. There's no infinite B. So as the area goes to 0, what happens to the magnetic flux? Go to 0. And what would that mean? A dot dl is 0. So in particular, A is continuous. See what's going to happen as the area goes to 0, the contribution is only from here and here. So we're literally getting A above and the z equals 0 plane. That's in our plane, we're picking that to be the xy axis for convenience. This is my z. So z equals 0 is where the surface exists, minus A below z equal to 0. And if you integrate that along dot dl, this is my dl right here. I'm getting 0 because the thickness has gone to 0 on this side. So that means A, and this is true regardless of the dl, so A above, when evaluated at z equal to 0, is equal to A below z equal to 0. On the xy plane, the A's agree. The A is continuous. Therefore, I can conclude this, regardless of what I'm doing. I'm going to conclude this and tell me why this is true. Component by component in, say, Cartesian coordinates. This is just math. Put that line too close. Why is this true? For every, see, partial derivative depends on how A changes when X changes. partial derivative with respect to x. But on the plane, for every x, a is the same whether it's calculated from above or below. Therefore, the partial derivatives also agree. What else agrees? There's another relationship like this. What could that be? Just to make sure that you understand the statement. So this is a purely math statement. This has got no physics in it. I mean, it has physics consequence, but there's another statement like this. What is that statement? What we're saying is, if I take the A above and A below, and you bring it here, it is same in the xy plane. Because it's same in the xy plane, regardless of how A changes along the x-axis, it doesn't matter if it's the numerator, the A above or A below. So their partial derivatives are the same. There's an exact same argument, a similar argument for a different direction. What direction would that be? That's it. It's the xy plane. Good. Yeah, the symmetry here is, all this production about z equals 0. It just means it is the xy plane where the actual current is. Okay? We'll unify this very nicely. In this problem right here, the way we've set up our coordinate system, the current is in the x direction. Which component of B is not continuous? Which one? X, Y, or Z? Y. So let's look at By. See, B equals del cross A. And is not okay. What is By? So here's my del cross A. X hat, Y hat, Z hat, dx, dy, dc, ax, ay, az. So by is the y component, which is what? Minus of minus, right? Yeah? So, you're asking, where am I going with all this? We know A is continuous. What I want to conclude is what happens to the derivative of A. Does that suffer any discontinuity? And it does. These are statements that are given in the book, and it says prove it as homework. So, but these are important things. That's why I'm showing it for you. So I have by above minus by below to be what? Minus mu0 k. Is that true? All evaluated at z equal to 0. In fact, so everything is at z equals 0. Yeah, because this is minus mu 0 k over 2. This is plus mu 0 k over 2, but with a minus sign. Minus and minus is minus, and the 2's vanish. So let's do this. That means minus dxaz plus dzax above minus dxaz plus dzax below equals minus mu 0 k. But regardless of the component, we know that the x derivatives and y derivatives are continuous. So then two terms cancel here. Which two terms cancel here? On the left-hand side.
Partials with respect to x.
Partials with respect to x. Follows from this one. And then I would have these are above limits and below limits, z equals 0, whatever you want to say. That's equal to minus mu 0 k. I want to make a vector equation out of this. Lack of space and board, I keep erasing. Are we good so far on this board? Look, first of all, this is x direction, this is x direction, k is in the x direction. So then I can do above, I'm not going to put this in, minus a below is equal to minus mu 0 k. Make sure that the minus exists, and it does exist. Yeah, it's a derivative with respect to z. That's a cooler way of writing it in the normal direction. That way it doesn't refer to any charge in the xy plane or anything like that. And by normal direction, what do we mean? It always means the same thing. It's the normal vector dotted with a gradient. So A is continuous, but the derivative of A in the normal direction suffers a discontinuity. It suffers a discontinuity in the direction of the current, but the derivative is normal to the plane.
So the direction of A is enforced by K?
Correct. Because this is it. This is the hard crank, the very specific. We picked an XY coordinate and we did the calculation. Okay, in a very specific coordinate system. We're trying to write it in a sort of a coordinate system that doesn't depend on X, Y, and Z. It looks more geometric in nature.
So, why would we cancel out those terms and not the others?
Remember we talked about how the X derivatives and the Y derivatives are continuous. So if you take the derivative from above, it's the same thing as derivative from below.
Yeah.
Yeah? We won't do much with it. I'm really doing it for completeness of discussion. It's still important as part of the subject material. This really doesn't enter into our problem solving. What we do use is the following. We're trying to understand how materials are magnetic. And just like dielectric materials, where we kept dipole moment, we want to keep, we had the monopole moment, the total charge, and the dipole moment. And then the higher moments exist, but they are less important. Or maybe they're important in certain materials, but that specialists who study the materials can provide those corrections. The difficulty is largely just bookkeeping. We know how to go about doing it. So we want to do the same thing to understand the origins of magnetism in a material. We'll keep up to the dipole term. When I say up to the dipole term, you should know by now, we've hinted this many times, the monopole term will not exist. Right? So let's do the actual calculations. And again, if you want to have more and more detail, you can put the quadrupole moment and all the higher moments of expansion. But you're thinking, you're telling me that, oh, wait a minute, all the monopole expansion, that was last semester. I have forgotten it. Sure, I have forgotten too, till I look up this morning. And as we do it, we'll recall. And it depends, but if it's part of your knowledge, if it's part of, if you've seen it once before, and if you have good notes, you can reconstruct it. Okay? So, with grandeur, I write multipole expansion, knowing fully well that I'm going to stop with the dipole moment. Based on the research that I do, I've never seen beyond the dipole moment. I don't study material science, right? But it still builds up a lot of intuition. So we could do it with a volume, but in most of the applications, we're interested in a current flowing through. So we have some I, and the electromagnetic vector or magnetic vector potential is given by correct? In some sense, this is not very difficult. We've seen this before. We just need an expansion of this guy. So let me set up coordinates. And as always, I give it enough space. So let me write my coordinates first. So you have a current loop over here, and then you locate any point over here by R prime, and there is a current DL prime. So there it is, I forgot the prime. And so this is R prime. And then, of course, is the point where you're interested in, far away, presumably, and you are calculating the vector potential at some point R. The whole point of multipole expansion is your currents are confined to a small region, and you're interested in finding an approximate expression for the current when you're away from the source. Okay? This vector, and the integration is done through all the prime variables. Currents form a closed loop. And the script R, as usual, is this vector. And we're going to assume that, well, magnitude maybe, huh? Because we're far away from any of these guys. So if we were calculating the the vector potential here, we cannot really use a multipole expansion. Again, think of a magnet or any molecule that has a magnetic moment. We're far away from the molecule. Yeah? In between molecules too, you can use this as an approximation. If the approximation fails, well, then we hang on to higher and higher order term. So this is what I need for you to recall. This is 1 over R, n equals 0 to infinity, R prime over R to the n, Pn of cosine alpha prime. Now what is alpha prime? Alpha prime depends both on R and R prime. And this is not easy to obtain at all. This guy is alpha prime. So any realistic problem you want to do, for simple geometries you can find clever tricks to integrate. For anything more significant than that, you write a code. Or nowadays, these things are already written, you just run it. So, I recall few things. P0 is what? 1. P1 is what? Cosine alpha, but I'm going to put it as alpha prime. I don't know what P2 is, but I wrote it down. I can assure you that we won't be using this. The first one will contribute to the monopole term. The second one, P0, will contribute to the monopole term. P1 will contribute to the dipole term. So let's do, instead of writing it out, let's write it out one by one. Naturally, we expect the monopole term to be 0. So I'm going to do A, one term, 0. I can bring out the I. Most often the current is constant. 4 pi. Lo and behold, what happens if you integrate this through a closed loop? The starting point and the ending point is the same point in a closed loop. As expected. Because, why as expected? Well, divergence of B is 0. So there's no 1 over R term in the magnetic case. In the monopole case, for the electrostatic case, this is not true. It's not 0. The monopole term is net charge divided by R, KQ over R. So let's compute the dipole term. Mu 0 I over 4 pi. I have this, there's this 1 over R, because when n is 0, you still get 1 over R. This is so R has an extra, just recall from last time, if R prime is to the n, r is to the n plus 1. Yeah. And here it's a dipole term, so when n is equal to 1, I'd get 1 over r squared. And then I have, what do I have? I have r prime cosine alpha prime dl prime. R prime cosine alpha prime can be written as r prime dot r hat. There's a problem towards the end in chapter 1 that I did in anticipation of this. It should be in your notes. Let me state the result. I certainly don't expect you to recall this. I think in the notation, let me look, I actually wrote it down so I don't mess this up. In the notation of problem 1.62, and I want to explain a couple of things. C is a constant vector, yeah? R and DL, because we didn't have any source, we were just doing math, we just called it R and DL. No problem if we call it that. C is a constant vector. What is the vector A? So here, C is a constant. I have derived this in class. Constant vector, and A is the area vector. Defined by, this is an interesting quantity. Yeah? Again, not that I want to spend time on this, we have discussed this. Suppose you have something like this. What's the area vector going to be? Well, it's going to be pi r squared z hat. Plus or minus, we don't know which one is the, no, it's defined only up to a direction. Correct? Area times the direction. If you have a sphere, what's the area vector? What direction?
Like radial.
It adds up to be 0. So you know, over here, this is my dA. For every point, there is this, and these two. So it's an unusual, just because we call it area vector, it's not magnitude of area times some direction. It is the actual net integral of the area vector. Fine. I, of course, have a habit of erasing very important things. Therefore, what we have is r hat, not C. And r hat is not being integrated over, so for us, it's a constant vector. So let me see if I can recall. A dipole is equal to mu 0 over 4 pi 1 over r squared current area vector across r hat. Define M, the magnetic moment by merge the area and the current. Then the dipole vector potential is mu0 over 4 pi m cross r hat over r squared. A very respectable looking expression. If you look at the dipole moment in electrostatics, there too you'll get a 1 over r squared. It is the same m that we have derived using a classical argument that appears in quantum mechanics as dipole moment, which is proportional to the spin of an electron. Intrinsic dipole moment. The electron is not a current loop, but there's an aggregate feature to it. Any questions?
So if we had a area vector, like we said, our sphere area vector was 0. So if we had some kind of spherical thing,
Yeah.
would that imply that our dipole term, would that be 0?
It could end up being 0. Yeah. If there's no preferred direction, then it
Yeah.
does go to 0. Yeah, absolutely. I have 3-4 minutes, and I just want to, make that look less abstract. What happens if you have a pure dipole, not a physical dipole? There's no loop. Pure dipole. Magnetic. So let me write this coordinate system. So here is the magnetic dipole, right? But it has an M that looks this way. So if you look at zero over 4 pi, I can't do anything over about 1 over r squared. Now m cross r, I know the magnitude. It's going to be m cross r hat. So it is m. It's a cross product, so it is sine theta. What is z cross r hat? Here's my hint, z cross r hat. Yeah, you get it.
That's the other way you're spinning.
Yeah.
And you gotta stop spinning so I can see what direction.
Right. So the only thing that changes direction is, you can check that out. Any Cartesian coordinates, m sine theta over r squared phi hat. This is if the magnetic dipole, picks a nice z-axis, but this is something we can visualize. If you look at your textbook, there's a diagram of what the A and B looks like. Well, how do you know what B looks like? Well, B dipole is del cross A dipole. And You can use any coordinate system you choose. You can use, because there's already phi hat here, you can choose spherical or Cartesian, sorry, cylindrical. And you pick the inside cover of your textbook and find out how to take the curl. And in fact, I would like for you to take the curl and verify, and I'm going to write this for completeness as we end the lecture, thereby ending the chapter so that you can take your eagerly anticipated exam, sine theta